Hey, Honors Physics, this is Mr. Hausman. We're looking at page number 5, and the topic of this is drawing electric field lines between and around different charged shapes. And we're going to take a look at charged plates as well as point charges, that is to say, like spheres. And we're going to talk about what happens when there's multiple charges or groups of charges on those objects. So let's start with the first example up here. Let's talk about parallel plates. So before you can talk about the final shape of the electric field, which I guess we could just memorize, we also have to remember that essentially the fields created by the positive plate and the negative plate, and why are they positive and negative in the first place? Maybe they're hooked up to a battery that has a positive and negative terminal. But what we remember is that for positive plates, even if this negative wasn't there at the bottom, they always point outward from positives. So I'm going to start at the positive plate and draw my field lines outward. Then I'm going to do the same on the bottom surface, and I'm going to keep them evenly spaced. And I'm going to draw right on through as if the negative plate isn't there. Okay? They look like they're longer, but in this case it doesn't mean they're stronger. Remember, the strength of the E field has to do with the spacing or the distance between the lines. So this is a uniform electric field. This is a uniform electric field. But they do go infinitely in all directions. We just can't show that. Now let's go into the negative and pretend that the negative is there, but the positive is not. So what would happen to the negative is that it would have electric fields that point inward on both sides. And we're going right through the positive plate as if it's not there. And this is basically referred to as the law of superposition. Superposition is really saying that the vector quantity of this case, the E field, is going to be the sum of the vectors of each individual object that's contributing to it. So here's a positive plate that's contributing red, and here's a negative plate that's contributing blue field lines. So if you were to analyze these and kind of figure out when are the fields adding up and getting larger versus when are they kind of adding up and getting smaller because they're the opposite direction, what you hopefully notice right here, let's focus in on this region. Do you notice that the blue arrows are going downward, the red arrows are going away, and that's true here and here and here and here. And I've tried to make it uniform, right? But essentially the red and the blue are opposite direction vectors, and the result is going to be that there is no field or minimal field outside on the top of these plates. Now let's look in the bottom region way down here. Let's examine what happens below the negative plate. Well, again, we have a red vector and a blue vector in opposite directions. They are going to cancel each other out, and so likewise, there's going to be no discernible electric field outside here because the red and the blue are canceling. But now let's examine the middle. Here, the red and the blue are actually additive. They are getting larger because they're both pointing in the same direction. The red and the blue are both pointing downward. So if someone said, what's the field strength, you would simply go in and say, well, the red and the blue are adding up to be a very strong electric field. Notice I'm maintaining even spacing between my field lines because that shows that it's uniform throughout. Excuse me. So that is the ideal version of a parallel plate, and this is called a parallel plate capacitor. And if someone says, what's the shape of the E field, you would say it's uniform between the two plates, but it is zero field, right? There's no field outside of the plates. Let's go back to point charges. If someone said, show me the shape of the electric field lines for these source charges, and these are pretty large Q values, so let's kind of start showing, okay, for any positive, they would point outward. And again, I'm going to try to maintain even spacing around the sphere. Now, if you count up how many field lines I drew, 1, 2, 3, 4, 5, 6, 7, 8, evenly spaced field lines, that kind of makes sense. There is no exact number, but what I've shown is an even distribution of the electric field. Now, this says that it's 3 times the charge. So you need to draw in 3 times the number of field lines, and they're going to become closer together. Now, if you're having trouble figuring out how to do that, you essentially have to fit in more field lines between all the ones you've already drawn. I'm not sure I'm going to be able to get all the way to 24 without messing this up. But there we go. Count them up. How many do we have? It's a lot more. Ideally, it's 3 times more. And you can also tell that this is a stronger field because the spacing between the field lines is smaller or narrower, right? How far is it between those vector arrows? And it's much smaller distance. So how would you draw a relative kind of like drawing for now a negative Q? And it doesn't say how large the negative is, but if it says that it's a negative, think of it as, but sorry, that's not a field line. Let me undo that. What we're getting at is that it's the same magnitude but opposite charge. So now, in theory, I guess we should draw the same number of charges. So 1, 2, 3, 4, 5, 6, 7, 8. Now, this one's negative 2Q. So if we're using the same system, it needs to have twice as many field lines because it has 2 times a stronger field. Twice the charge is going to generate twice the field. So now we have to double our line. So instead of having to try to fit in 24, at least now we only have to draw in 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, I still ran out. And my drawings are not necessarily the best. Your arrowheads can probably be controlled a lot more easily on pencil, on paper, than with the stylus. But that's one of the key ideas, that the amount of charge determines the strength of the field and how you draw the field lines. Now, we've seen this one before. It was on a previous page. These are no longer discrete. What I mean by that is these 2 charges are no longer isolated single charges. These are 2 charges which are relatively close to each other, and we do the vector addition. So they come out of positive. They go in towards negative. And then in between the 2, they go out from positive but in, and so this is 2 vectors essentially adding up together. Remember, we used red and blue before, and so it's making it stronger in the middle. Then we would have a blue one going out on a diagonal, but it can't cross the red, and those would eventually cross. So what we get is a curved field line, and here's another curved field line, and they would keep curving. But they go, right, the source, they always are drawn from the positive, coming out of the positive, and they go in toward the negative. So this page is kind of a few questions about how would you analyze the relative strength, or how would you interpret these diagrams. So I see 3 separate diagrams, and what I notice is that as you go from left to right, the field lines are increasing in number, the spacing is decreasing. So we know that they're all positive because in every single one, the field lines are pointing outward. But if you were to kind of go from 1, 2, 3, 4, 5, 6, 7, 8, and then count how many are here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, that's twice as many field lines, so that would be twice the amount of charge. And I dare say this is probably 3 times the charge. So it's, if the first one was positive 1, the others are 2 times that, and probably 3 times that. So in the picture next, in this next question, several of the field line patterns are shown, but some of them are incorrect. And let's kind of examine what we might mean by incorrect. So are the field lines pointing in the correct direction? Are they evenly spaced out? And the answer looks like, diagram A looks pretty solid. It looks just like the one above. B looks like one that we had on page number 5. Let's take a look at diagram C and see if you can notice what might be going on. We have a positive source charge, but the arrows are pointing in. And That's incorrect. That is not the correct convention. The field lines are drawn out of positive. D, problem. Why are they unevenly distributed? So if you said because there's another charge nearby, we don't know that. They are not, diagram D is a single point charge, and there seems to be an overabundance. So it's almost like the field lines are stronger on one side and weaker on the other, and that's not true for a point charge. Okay, how about E? Do you like E? E looks right. It looks just like A, except for it's the wrong direction. Negative charges, the field line should be pointing inward. So Aaron again, funny but not funny name, drew the following field lines for a configuration of two charges. And we saw that in the first video, that when field lines are coming out of two positives and they're starting to kind of come at each other, they tend to want to cross. And that's exactly what Aaron drew, and that's wrong. So field lines, let's clean that up. Field lines should not or do not cross. And the reason why they don't cross is because that would say that when they're adding, they're during the vector addition, during the superposition, they're adding up and they're kind of creating, they should be getting smaller, but in fact they are getting larger. So the better shape for this would be, if I were to kind of highlight this, let me see if I can change that and make it, and kind of hide those lines, and let me draw them in. Well, they still bend toward each other, but they bend toward each other in a way that never crosses. For those of you who may have seen this in math class, it's as if they reach an asymptote, a limit, like on the y-axis, but they never cross each other. So that's a pretty good math connection to make. Let's go to the next one. Consider the field shown in the diagram below. From the diagram, it is apparent that object A is what? Well, object A, all the field lines are going inward, so A has to be negative, and they're coming out of B, so that must be positive. So what choice is that? That is D. So object A has to be negative, and object B has to be positive. So D answers number 3. Now, this is something new, and I'm going to save this to another video. So that's the end of the examples, and we're going to talk a little bit about fields around conductors or conducting metal objects, what's inside, what's outside, in another video. But that should help with page 5 and 6.